As some of you probably already know, the spin-foam framework is an attempt to construct a well-defined expression for the Pareto integral in the case of quantum gravity. In the loop quantum gravity perspective, we usually start with a discretization of the F-theory. We quantize that discretization, and we implement a set of constraints at the quantum level to try to reduce the theory to a quantization of general relativity. That procedure defines a spin-foam model. The EPRL model is the most accepted spin-foam model in the loop quantum gravity community because, among other things, provides well-defined expression for transition amplitudes. And this expression is very successful when we compute quantum effects in some physical situations, for example, in some cosmological scenarios and in space-time singularities. Also, this expression has a well-defined discrete semiclassical limit, which is related with the Regge action. Taking into account the success of the EPRL model, it is natural to ask, why a new perspective? Well, a more detailed account of the spin-foam framework will reveal that the reasons could be various. In the standard construction, there is a discrete tetrad at the classical level, but there is not analogous at the quantum level. Also, the standard construction relies on the use of flat forcing pieces glued together to recover curvature. And for this reason, the role of the curvature at the quantum level have been barely tested. On the other hand, the set of constraints that define the EPRL model can be divided into first and second class constraints. And there have been some concerns about the consistency of the implementation of the constraints at the quantum level. Regarding this last point, there have been some responses where they said that the implementation is actually consistent and provides a well-defined quantization of discrete general relativity. However, even with this, it is natural to ask, well, there is an alternative construction about identity stages, especially if we are able to introduce tetrads at the quantum level. Regarding all these questions, my purpose is to introduce a new perspective to construct spin-foam models that try to shed some light in some of these issues. As a first step, we revive the use of a structure that is called the derived complex as a tool to discretize the differential manifold. This structure was previously used by Reisenberger as a standard tool to define spin-foam models. We start with an oriented simplicial complex in 4 dimensions and its corresponding dual. The intersection between a 4-simplex and a bidimensional cell of dual is called a wedge. The intersection between a 4-simplex and a 4-dimensional cell of the dual is called a corner cell. This diagram shows the structures in the case of 3 dimensions. Of particular importance for us are the edges of the boundary of the wedges. The lines L connect the barycenter of a 4-simplex with the barycenter of a tetrahedron at the boundary of the 4-simplex, and the lines R connect the barycenter of a tetrahedron with the barycenter of a triangle at the boundary of the tetrahedron. Once an orientation has been selected, we associate an element of a Lie group, in the Lorentzian case, an element of SO31 to each line L and to each line R. And this provides a discretization of the connection. We also associate an element of the Minkowski spacetime, an element different from 0 to each line L, and this provides a discretization of the tetrads. These associations help us to have an element of the Lie group associated to the boundary of each wedge. And this provides, this quantity is closely related to the curvature of the continuum theory. With all these associations, we define a classical discrete model with an action given by this expression. In this expression, theta is essentially a discretization of the curvature 1 form of the continuum theory. T are the generators of the Lie algebra, and P is a quantity that is constructed using, among other things, the immursi parameter. SGN is essentially the sign of the 4 volume generated by the wedge S and the lines L. Under some mathematical assumptions, it is possible to prove that this action actually converges to a form of the whole section in the continuum limit. The model where the basic fields are the E, the H, and the K is what we call the E model. The E model has some very interesting characteristics. For example, the basic fields are the E, the H, and the K. We can associate a discrete tetra to each corner. and we can easily write the action in terms of this tetrad. Also, we can associate a discrete metric for each corner with the characteristic that the metric of two corners in the same forcing plex agree on the three-dimensional subspace where they intersect. Also, the model is defined using a discrete tetrad field, and for this reason, there is no need of simplicity constraint to define it. Also, in this model, we can write functions of the space of stories. Specifically, we can write expressions for geometric quantities like areas and volumes in the bulk of the discretization. The classical model presented above can be formulated as a constrained BF theory. If instead of a discrete tetrad, we start with an association of an element of the Lie algebra to each wedge, we can impose a series of conditions over that field, and to prove that in the non-degenerate case, we are able to recover the discrete tetrad field. This defines what we call the B model, and in this sense, we say that both the E and the B model are classically equivalent. This set of constraints, the first one is pretty similar to the standard linear simplicity constraint that is used to define the EPRL model. In our case, it states that for each line, for each forcing plex and for each line L inside of it, there exists a non-zero vector n of the Minkowski spacetime, such that the construction between that n and an element B is 0, but that element B is associated to a wedge such that the line L belongs to the boundary of S. The second constraint essentially says that the volume of a corner is independent of the couple of wedges that we use to calculate it. And the third condition is a condition for the signature of the discrete metric that can be constructed using the B field. In the B model, the basic fields are the B's, the H's, and the K's. And for this reason, we can form a discrete metric density using the B field. Also, the model is written as a constrained BF theory, and for this reason, we can follow a standard spin-foam quantization procedure to formulate that spin-foam model. Both models, both the E and the B models, have some very important shared characteristics. The first one is that the boundary of data are the boundary connection and its conjugate momentum. Also, in both models, we have a well-defined both bulk and boundary geometric seating, and this allows us to study correlation of geometric observables. In both models, there is a natural way to regularize matter couplings, especially because of the existence of a discrete metric. However, the most obvious characteristic of our proposal is the existence of curvature inside each forcing plex. In the standard ray G discretization that underlies the EPRL model is constructed using flat pieces glued together to recover curvature. And only very recently, the first simulations involving more than one forcing plex have been performed at the quantum level. One example is the reference presented here. This means that the curvature degrees of freedom have been barely tested in spin-foam models to quantum gravity. On the other hand, in our proposal, even when it cuts the degrees of freedom, the forcing plexes are not flat. And this means that the quantization of our models will necessarily include curvature degrees of freedom at the level of one forcing plex. The spin-foam quantization of our models follows some of the same steps than for the rest of the models. We start with a partition function written as an integral of the action, of the exponential of the action over all the configuration of the fields. In the case of the B model, we can easily isolate an amplitude associated to each forcing plex, what is called the vertex amplitude. All this is, however, a word that is still under construction. For the BF par, we can calculate the integral over the B field and give an explicit formula for the vertex amplitude. For the Euclidean theory, which is the SO4 case, we can actually recover the standard quantization of BF theory. This is nice because we know that quantization of BF theory is independent of the discretization. The implementation of the constraints, however, requires to be able to identify an amplitude associated to each corner and to glue that amplitude to recover the original vertex amplitude. This is so because the classical constraints that define the model are such that the U element, the conjugate moment associated to the boundary, it comes from the wedge product of two elements of the Minkowski spacetime, only when we restrict to each corner. So if we want to be able to justify the implementation of the constraints at the quantum level as in the standard spin-foam quantization procedure, we need to be able to study the action of such constraints on each corner. All this is, in our case, however, a work that is still under construction. So in this talk, I have tried to present to you an alternative to construct spin-foam models that tries to explore some characteristics that, while they are not necessarily absent, they are not direct or explicitly accessible in the standard construction. In our case, there are a lot to explore. We need to explore with more detail the quantization of both the B and the E model, and what is the relations of both models at the quantum level. Also, it is important to consider the role of the matter coupling, especially because of the existence of the discrete metric and the effects of the curvature at the level of a single force simplex. Last thing I would like to mention is that there is actually another B model where the constraints are different, but that is classically equivalent to the B model presented here. This B model was originally constructed for convincing researchers that it can be used to construct an even more numerically efficient, effective spin-foam model, but with superior gluing properties. For more details, for an exposition of the B model not presented here, and an exposition of even more nice characteristics of our proposal, you can check the reference presented in this slide. Thank you.
Okay, thank you, Carlos, for being on time. Questions, please?
Nobody. Everything is clear. That's a very bad signal.